Okay, so this is the 2019 paper. So it's the second time that the paper was published, and the last time it was published before the lockdown. Okay, so this is the higher tier. So let's have a look at question number 1. So question 1 tells us that crude oil can be separated into simple mixtures called fractions, which contain hydrocarbon compounds with boiling points in a similar range. Okay, so just to be clear, hydrocarbons include the alkanes and the alkenes rather, and they are chemicals that consist only of hydrogen and carbon. So if I have a look at the table, I just need to pause for a second to apologise. If you can see the flickering, I've tried to stop it, but there's something going on here. So we'll just have to push on through. So it tells us that fuel oil, okay, has 1 to 4 carbon atoms in the molecules in this fraction, and it boils between -70°C and 20. It's colourless, it burns with a nice clean flame, and it's very easy to burn. As we move down the table, basically, as we look at different fractions, the molecules get bigger because they've got more carbon in them. Their boiling point increases, so as the molecules get bigger, they need more energy to turn them from liquid to gas, and they get increasingly dark. Okay, so they go from a colourless all the way through to brown. The flame, when burning, becomes more and more sooty or smoky, and it gets more and more difficult to light them as the molecules get bigger. Okay, so use the information in the table to describe how the burning of the fractions depends upon the size of the molecules. So we've got to make 2 comments because there's 2 points, or 2 marks rather, and we can take information from these 2 columns here. So we can say that the flame becomes more smoky as molecule size increases, and larger molecules become more difficult to light. Okay, so you could word that slightly differently. You need to make both those 2 points there. Okay, now moving on, we've got here the boiling points of the hydrocarbons containing 1 to 12 carbon atoms are shown in the table below. The boiling point for the hydrocarbon with 7 carbon atoms is missing. Okay, so these are the hydrocarbons, more than likely the alkanes. So this is methane, ethane, propane, butane, pentane, hexane, septane, octane, and so on. Okay, and as we can see, the boiling point starts off very low, and as the molecules get bigger and bigger, the boiling point increases, which agrees with the information up here. We've then got a graph that we need to fill in. So usually this is a bar graph. Okay, so and the reason it's a bar graph is because there are no intermediates between each of these values. So even though these are numbers, they are integers. You can't have 2.5 carbon atoms or 3.7 carbon atoms. So we're forced to plot a bar graph. But like most graphs, okay, it's quite generous here. There's 2 points for this, okay. So you need to put the data on here. So 2 carbon atoms is -90. Okay, so each of the we need to leave a gap between each one, okay, and then -90. So -90 is going to be here. Okay, so we're going to draw var, leaving a gap between each of the bars. Then we've got -40. Okay, so -40 is going to be here. And then we've got 10. Okay, so 10 is going to be there. And then for 5, we've got 35. Okay, and there's 25, 35. And then for 6, we've got 70. Okay, so 70 is going to be 4 squares above. Be a little bit slapdash here. Let's use a ruler. Okay. And so just so that we're clear there, I'm not very proud of my 6 carbon bar there. Okay, but trying to get this done as quickly as I can. Okay, so basically, as long as you plot them accurately, you're going to pick up the 2 marks there. It then says use a ruler to draw a trend line on the chart and use this to estimate the boiling point of the hydrocarbon with 7 carbon atoms. So not something we do very often, but drawing a trend line through the bar chart. Okay, so we're trying to skip through the top of each of the bars. Okay, so we'll use the ones that are published for us. We'll try to skip through the top there, and that would give us our boiling point of number 7 around about 90 degrees Celsius. Okay, so approximately 90 degrees Celsius. Okay, is what we're looking for there. Okay, and the acceptable range was actually between 85 to 105. Okay, so that's the first page complete. Okay, so if we move on now, it says here that many fractions obtained from crude oil are used as fuels. Okay, the fire triangle shows the factors necessary to start and maintain a fire. State one method that can be used to safely put out a small amount of spilled petrol burning on the floor. Give your reason why your chosen method would work. So the fire triangle, okay, and we'll just sketch it down here, requires a fuel. It requires a heat source. And it requires oxygen. So basically, any means of removing one of those 3 items will put out your fire. Okay, and possibly the most popular one is to remove the oxygen. Okay, so removing oxygen, we can douse the fire. Okay, to cover it, douse or cover. Okay, and so we could use sand or foam. It's not a good idea to use water as it happens, because water tends to splash the liquid fuel around. Okay, so that would remove the oxygen. You could also use a fire blanket. Those 3 methods there would remove the oxygen from the fire triangle. Okay, and therefore put out the fire. In the case of a small fire, on a forecourt in a petrol station, it's difficult to remove the heat source because that's already set the fire off. And removing the fuel again, you would obviously turn the fuel off, but often we use sort of water to spread out the fuel, but that would make the matters worse. So these 3 here would be the best. So if you just put them in the appropriate place. So we're covering with sand, foam, and those remove the oxygen. Now, that's the best method in this particular instance. If you can, some fires it might be best to remove the heat, and some fires to remove the fuel, but in this particular instance, remove the oxygen. Okay, so one of the hydrocarbons in petrol is pentane. Okay, so that's C5H12. So just as a double check, we'll see, does it fit the bill? Is it indeed a alkane? Okay, so I'm just checking. So double 5 gives you 10 hydrogens, plus the 2 gives you 12. So it does fit the general formula. Complete and balance the symbol equation for the complete combustion of pentane. Okay, so we've got here boxes and spaces. So that tells us that we will need to put numbers in here, and we do need to come up with the formula. Okay, so when we burn things, generally speaking, we're going to get carbon dioxide and we're going to get water. So those are the 2 products of combustion. And if we look at the number of carbons in pentane, we can see there are 5 of them, And the only place that carbon turns up on this side of the equation is in carbon dioxide, so there must be 5 of those. And then if we look at the hydrogens, there are 12 hydrogens altogether, and there's 2 in each water, so that tells us there must be 6 H2Os. And if we double check this, just cross check it, so we know we've got the carbons and the hydrogens right, because that's how we've come up with these 2 values here. We've got 16 oxygens on this side. On this side, we've got 5 times 2, which is 10, plus 6 times 1, which is 6, obviously. So 10 and 6 is 16. Okay, so we've got 16 on this side and 16 on this side. So that's okay, that's balanced. And 2 marks for that. Okay, hydrogen fuel cells are now used in many cars instead of petrol. The overall change inside a hydrogen fuel cell is the same as when hydrogen burns. Okay, so when we say burns, we invariably mean reaction with oxygen. Explain why using hydrogen fuel cells in cars is better for the environment than petrol. Well, basically, when you burn hydrogen, you are reacting it with oxygen to release energy, and the only product is this stuff here. Okay, so we need 2 of them and 2 of them, and so the only product is water vapor, which is significantly less harmful to the environment than the carbon dioxide produced here. Okay, so it's water vapor, no CO2, better for the environment. So it doesn't add significantly to global warming and therefore to the climate change that we're experiencing. Okay. Right, moving on to part D. Okay, so this should be a familiar experiment. This is one of the specified practicals. There's a slight variation on, but it's similar to the practical that you will have done. It is possible to compare the energy released from different fuels by burning using the following apparatus. Okay, so we've got a container with some fixed mass of water. Don't forget that the density of water is 1 gram per centimetre cubed, so that's equivalent to 100 centimetres cubed. Okay, that'll be how it's actually measured out, is by volume. Then we've got a spirit burner, which is a container has got your fuel in it with a wick, and we can use this to deliver the heat energy relatively accurately to the bottom of the beaker. Now, this calculation here is similar to the one on your specified practical, but they do give it to you in the exam, so you don't need to memorize it. So to calculate the energy released per gram of fuel burned, the following equation is used. Okay, so the amount of energy is the mass of water, which is given to you in the question, times 4.2, which is a magic number. It's a specific heat capacity of water, but you don't need to know that. You just need to make sure you include it in your calculations. Multiplied by the temperature rise. Okay, so it's not the temperature, it's the rise in temperature, and the mass of fuel used. Okay, so you need to be careful with those 2 there, that you understand how to get hold of them. Okay, I don't really want any new software from Apple, to be perfectly honest. Let's go away. Right, so apart from measuring the mass of water, describe all the measurements that you would need to be taken to be able to calculate the energy released per gram of fuel burned. Okay, so we've got 2 marks for this. So we need to specify that we need the temperature rise. So we need the start temp. Before you do the experiment, you need to measure the temperature of the water before you light the fuse, and the end temp, and that will give you the temperature rise. Okay, so if you take the start from the end temperature, I should have used an ampersand there rather than a plus sign. So start temperature and end temperature, and that gives you the temperature rise. Because if you take that value from that value, you'll get an increase in temperature. And you also need the start mass of the spirit burner and the end mass. Now, if all goes well, your end mass will be less than your start mass, because the fuel will make its way up the wick, burn, and turn into carbon dioxide and water, reducing the mass of the spirit burner. So it will get less and less. So that will give you your fuel used. The difference between those 2 values gives you your fuel used. When comparing the energy release from different fuels, 100 grams of water should be used each time. State one of the variables that should be controlled. Okay, so going back to these here, it's useful to have the same start temperature. So each time you do the experiment, you refresh the water, so it's the same at start temperature, to ensure that you've got a fair test. Okay, because it's you don't really want the start temperature to be different each time. Might also be wise to have a look at this distance here. Okay, so make sure that you don't adjust the height of your container so that the distance between the burner and the bottom of the beaker are the same. Okay, so same gap, because the flame energy has a tendency to sort of disappear off into the room. So you want to try and minimize that by keeping the gap the same, so at least you're consistent. Okay, and as it's quite popular, we've got these energy profiles. Now, this is an exothermic reaction. Okay, I think if you put your hand over the burner as it was running, then you'd soon learn it was exothermic, gives heat out. So that means that the reactants are at a higher energy than the products, because they release energy into the surroundings, into the environment. Okay, so consequently, this one here is the reaction progress. So it starts off with the reactants at a higher energy. There's a bit of activation energy to get over once you light the wick, but once it's lit, and the products are at a lower energy. Okay, and therefore that difference there is the energy that we experience as the air getting hot, or the water getting hot in this particular experiment. Okay, number 2 deals with bonding. Okay, so it says here that magnesium reacts with oxygen to form magnesium oxide. Now, in order to make a decision as to what sort of diagram you're going to draw, you need to establish that magnesium is a metal and oxygen is a non-metal. If you're not sure, it's always wise to check in the periodic table. So if we turn to the periodic table at the back, just check. One little trick you might want to do before you actually start your paper is just to draw that zigzag line, that staircase between the metals and the non-metals, just so you're absolutely clear. There is a bit of a blurred area between where we've got the metalloids, but in most instances this zigzag line or staircase will differentiate between the two. So it starts off between boron and aluminium, okay, and then it just goes down there. So magnesium is way over here, so it's very metallic, and oxygen is here, which is non-metallic. Okay, so having established we've got a metal and a non-metal, we need to remember that tells us that we've got ionic bonding going on. Ionic bonding. So in ionic bonding, we need to show the transfer of electrons. Okay, it's not a sharing of electrons; it's a transfer of electrons. And whilst we've been given the full electron configuration of both of them, it's usually acceptable just to do the outer shell, or possibly the outer 2 shells. Okay, because magnesium, and for the sake of complete clarity, I'll draw the whole thing, but you could get away with not drawing the inner shells. So magnesium is 2, 8, and then 2 on the outer shell. Okay, so we've got 2 electrons on the outer shell. I've deliberately put them on this side of the diagram. Okay, because what magnesium, being a metal, tends to do is to give its electrons away, to lose electrons to oxygen. Oxygen is 2, 6. Actually, I'm going to draw dots for the oxygen electrons. This is simply to show where the electrons can't stick to dots. So in this part of this diagram here is showing the transfer of these electrons across into the oxygen. Okay, and then the convention here is to draw the aftermath. So this is supposed to be an arrow. Obviously, I'm going to draw the aftermath underneath. What we tend to do is draw square brackets, and then we're left with a magnesium, which has now only got 10 electrons because it's got 8 in the outer shell, and it's still got those 2 in the middle which are unaffected. And because those are unaffected, that's why we can sometimes get away with not drawing that inner shell. Because it's lost 2 electrons, it's become 2 plus. And then the oxygen, again, those inner electrons are unaffected by all this, so we didn't really need to draw them. But this now has got its original 6 electrons, but it's now acquired 2 from the magnesium, and consequently, because it's acquired 2 electrons, it becomes 2 minus. Okay, so just double check that we've done all we need to do, because we've got 3 marks here. So we use the electron structure to draw dot and cross diagrams to show how bonding takes place. So this is the taking place to form magnesium oxide, include the electronic structures of the ions formed. Okay, so we've done that, and we've also included the charges. Okay, so we need to draw this sort of 2-stage diagram because it's ionic, because we've got a metal and a non-metal, and the electrons are transferred from the metal to the non-metal. Okay, this second question, part of the question rather, says the melting points of magnesium oxide and sodium chloride are given below. So sodium chloride is 801 and magnesium oxide is 2852. So both these values are relatively high, but clearly this one's much higher than that one. Okay, and they're both high because ionic compounds have strong inter-ionic attraction. The negatively charged ions and the positively charged ions are attracted to each other. The difference, though, is if we look, we've already established that this is Mg 2 plus and 2 minus. If we just quickly nip to the table of ions in the back here, we'll discover that sodium is only 1 plus and chloride is only 1 minus. So that the size of the charge is half. Okay, so both relatively high due to ionic attraction, between oppositely charged ions. However, MgO consists of 2 plus and 2 minus ions, therefore higher attraction. More attraction. Okay, so the double charge in both instances makes the attraction between the ions even greater, which is why we have this inflated melting point. Right, now this next part of the question, we need to be careful. So using the electronic structures below, draw a dot and cross diagram to show the bonding in a molecule of carbon dioxide, which looks remarkably similar to the previous question. However, the subtle difference is that carbon dioxide, CO2, these are both non-metals. So they're both non-metals. And consequently, we need to show a slightly different sort of bonding, and that's covalent bonding, where we share electrons. Okay, so if we draw the carbon with its 2 electrons in the first shell, and then 4 electrons, I've drawn this slightly skew, but never mind, 4 electrons. Now, we're not going to draw the electrons just yet, because it will need another 4 electrons. Okay, needs another 4 electrons to get a full outer shell. Oxygen, okay, needs another 2 electrons. So what I should have done is draw my carbon in the center of the page to make things slightly clearer, but we can get away with this. So the oxygen has got its 2 electrons, which I'll draw as dots in the first shell. And then because this is a covalent diagram, we have to make sure that our electron shells overlap. Okay, and I've drawn these deliberately quite a big overlap because I know that I'm going to have to draw 2 crosses belonging to the carbon and 2 dots belonging to the oxygen. So for this outer shell, I've drawn 2 of the 6 electrons. So I need to draw another 4 here. So if we just double check that everything is correct, the oxygen is 2, 6, so 1, 2, 3, 4, 5, 6. And then on this side, we're going to repeat that process because it's CO2. So we need the inner electrons, 2, And then again, we're going to put 4 electrons which don't take part in the bonding, and 2 electrons that do take part in the bonding, and then the other 2 electrons belong to the carbon. So the carbon now has 1, 2, 3, 4 electrons on its outer shell of its own, but if we include the ones from the oxygen, it's got 8, and then each of the 2 oxygens also has a share of 8 electrons. And so with these 2 shared pairs of electrons, we could represent this in a different format like that, but this particular question wants a dot and cross diagram. Okay, so we must make sure we draw a dot and cross diagram. Okay, so that's the end of number 2. Now moving on to number 3. Okay, so this question is taken from the metals topic, or extraction of metals, and again it's an example of electrolysis. However, they've used electrolysis to illustrate another feature of chemistry, which isn't specifically in the syllabus. However, it is explained in the question. So it says when 2 different metals are connected in a cell, okay, so a cell is where you've got 2 electrodes and an electrolyte, the metal with the higher reactivity transfers electrons to the other metal. Okay, so it's not dissimilar, I suppose, to what's going on here, but we've got 2 metals involved. So a metal of higher reactivity will transfer a metal of a lower reactivity in this situation, depending on what these 2 electrodes are made out of. Now in this particular cell, 1 electrode is made out of copper, and then we vary the other electrode. So depending on the reactivity of this metal, the electrons will either go from the copper towards the other metal or the other way. So it tells us each metal was placed separately into a cell with a copper strip. The potential difference was recorded for each metal, and the results are shown below. Okay, so the potential difference there gives an indication of how easy or otherwise it is for that electron transfer to happen. Okay, so we need to bear those in mind and have a look at the information here. So it tells us that for metal A, electrons are transferred from copper to metal A. So given the information in the question, okay, where it tells us that the metal of higher reactivity transfers electrons to the other metal, then copper must be more reactive than metal A. Okay, and we can see the same is true for metal D. Okay, so these 2, so A and D, are both less reactive than copper. Okay, the extent to which that happens is the potential difference. So it only happens to an extent of 0.3 with metal A and to 0.8 with metal D. So that tells us that metal A is here, because we know it's less reactive than copper because of this information there, and the number tells us by how much. So this must be D. Okay, and then looking at the other 2, so metal B will transfer its electrons to copper by 0.6, and metal C will transfer its electrons to copper by 1.1. So it's better at it because it's got a potential difference of 1.1. So that tells us that C lives here and B lives there. Okay, because it's more reactive. So this tells us whether it's more or less reactive, and this tells us by how much. Okay, so we've got BC, AD. So that's a bit of unpicking a puzzle, really, okay, because you're given the information in the question as long as you can interpret it appropriately. Okay, so a little bit tricky, but possible, I think. So we've also got B. Okay, so this is a similar theme. The reactivity of 4 other metals, W, X, Y, and Z, was also investigated using the same apparatus. Some of the rules are shown below in the table. Okay, and then the order of the reactivity is given to you. So if we have a look at the information we've got in here, okay, we know that the direction of flow is W to X. Okay, so that's the more reactive metal, which makes sense because W is above X in this reactivity series, and that happens to an amount of 1.2 volts. Okay, so the transfer of electrons there is 1.2. Here it tells us W and Y, the transfer is from Y to W. Okay, so Y to W, and that is the potential difference is 0.9. So Y to W, sorry, y to w rather, is 0.9. And then we've got this one, the last one, sorry, y and z, okay, is y to z to an extent, and we're not given that, okay. So y to z we know is down there, but we don't know by how much, okay. And we know that w and z is, well, by inference, it's going to be z to w and it's 0.8, okay. So it's going to be z to w, and that's going to be 0.8, okay. So we can work that out because the reactivity series is given to us here, and we're given the value of 0.8 there, okay. So so it uses information to give the direction of electrons when w and z are placed in the cell, okay. So we can simply repeat what we've written here. We can say z to w because of the reactivity series given us in the question, and then what's the potential difference for the cells y and z, okay. So y and z are here. So if we know that the potential difference between z and w is 0.8, okay, because it tells us it in the question, and we know that the potential difference overall is 0.9, and that difference there must be 0.1, okay, because the total potential difference will add up to the value of 0.9. So that's going to be 0.1 volts. Okay, so again, a little bit of a puzzle to unpick, okay, but the information is there for you in the table if you just take a few seconds to sort of unpick it. Now, this last question on the same topic, okay, when copper and zinc are placed in the cell, the following reaction takes place. So we can see that the 2+ ion is reacting with the zinc, and we end up with a zinc 2+ ion and copper. So if this here becomes positive and this becomes neutral from being positive, then if we look at these, the previous question, we know that the electrons are moving from the zinc to the copper, okay, because that neutral zinc becomes positive, and that's because it's lost electrons, it's given electrons away to the copper, and conversely, the copper has gained electrons, okay, it's gained electrons from the zinc. Now, if we remember the little mnemonic oil rig is how we can remember what's going on in terms of redox reactions when we consider electrons. And if you remember, it stands for oxidation is loss, and reduction is gain. And this is talking about electrons. So if we look at the species here that's lost electrons, zinc has lost electrons, okay? So it's been oxidized, and copper has gained electrons, so it's been reduced, okay? So the zinc loses electrons, so it's oxidized, and the copper gains electrons, so it's reduced. So to answer that question, you do need to remember oil rig, and we're talking about redox reactions, okay? Redox being oxidation and reduction combined into one. Okay, number 4. So number 4 is taken from the acids and alkalis topic. Okay, you can see our friend the burette down here. Okay, so in a class experiment, Dylan and Joel were given a solution of sodium carbonate containing 5.23 grams of sodium carbonate powder dissolved in 500 centimeters cubed of water. The relative formula mass for sodium carbonate is 106. Use the information to calculate the number of moles of sodium carbonate in the 5.23 grams of powder. Give your answer to correct to 2 decimal places. Okay. So, in order to answer this question, we could do with remembering a bit of a triangle. Okay, there's a couple of triangles that are handy in these situations. Okay, so we need to remember that the MR, okay, or moles per gram, moles and grams, okay, are, sorry, my mistake, grams per mole, grams, I'll do it again and make it clear. We get that? So grams, mole, and the MR, which is in grams per mole. So with that in mind, okay, we can use the values given to us in the question. Okay, we're told that there's 5.23 grams of sodium carbonate, so that would be the grams. So 5.23 grams. Okay, and then divide that by the MR. The question asks us for the moles. Okay, so just make that clear. So we want to know the number of moles of sodium carbonate. So to get the number of moles, we need to take the mass and divide it by the MR. So we're given the mass in the question and we're given the MR in the question. So 106 grams per mole. Okay, and if you do that calculation, you get grams cancel and the moles come to the top. Okay, so and that gives us a numerical answer. Let's pull that through the calculator. Go on, calculator. So 5.23 divided by 106 gives us 0.049 blah blah blah, but it does say in the question to 2 decimal places, so that rounds up to 0.05 moles. Okay, so it then goes on to say Dylan and Joel were asked to use sodium carbonate solution to prepare a sample of sodium sulfate crystals in a 3-stage process. In the first stage of their preparation, they used the following apparatus to carry out a titration. So we've got here sulfuric acid, and we've got the sodium carbonate indicator, and you're told here the reaction going on in the flask. So this is a carbonate reacting with an acid, which makes a salt, water, and carbon dioxide. And this is the salt that we're after. Okay. So they did a trial run was carried out, and the titration was repeated 3 times. The volume of acid added each time was recorded. So in the trial run, they added 30.2 centimeters cubed of acid. But once they'd got the idea, they then added 27.55, 27.75, and 27.65. So as might be expected, these values are lower than the trial because by this point they know how much they need to add. So state the purpose of carrying out a trial run. So this is to establish the approximate volume of acid required. Okay, so the first time you do it with the indicator, you're not quite sure where you're getting to, how much you need. So you do a trial run so that you know when to slow down for your subsequent titrations. State whether the sulfuric acid or the sodium carbonate solution is the more concentrated. Give the reasons for your answer. Okay, so if we have a look at the volume of sodium carbonate solution used each time, so every time we start with 25, and then we look at the volumes of the acid, then we can see that we need more acid to neutralize the sodium carbonate than sodium carbonate. So that tells us that the sodium carbonate is more concentrated, slightly more concentrated. It's not a big difference. It's 25 centimeters compared to the 27. But it's slightly more concentrated. Okay, because you need a little bit more. So the sodium carbonate is more concentrated. Okay, and there's just the 1 mark for that. So don't think that they're expecting you to give any more reason than that. Okay. Now, use all the information provided to describe in detail the other two stages Dillon and Joel carried out to obtain the pure sodium sulfate crystals. Okay, so it says in the introduction it's a three-step process. Okay, so we need to, three-stage process. We need to detail two more steps. Okay, so step 2 is to repeat titration without an indicator. Okay, because you don't want your final product to be contaminated with indicator. Just slow down. I'll slow down and spell it properly. Indicator. Okay, so that's to remove contamination. So the indicator itself would contaminate your final product. So you would do it on trust, if you like. You know how much you need. You would take an average of these three, and then you would use that volume of acid against 25 centimeters cubed of sodium carbonate, and you would get the fizzing produced by the carbon dioxide, but you wouldn't get any color change. But you would be confident that you've added the right amount. And then stage 3, okay, all this being stage 1, is that you would then evaporate the water. So you could do that using a Bunsen burner. Okay, so but you would be wise to only partially evaporate off the water with a Bunsen burner. Leave it for natural evaporation to get better quality crystals. So when we've done something similar, we left it on the windowsill for a while to get the copper sulfate, I believe it was. Okay, so you drive up some of the water, but then allow it to evaporate naturally. Okay. At this stage here, I think it's probably important that you do mention that you use 25 cm cubed of the carbonate. And then the average of these three values here, if you look at them, is 27.55, 27.75, and 27.65. So the average of these three values is actually 27.65, because that's in the middle. So 27.65 cm cubed of acid. Okay, so that's using the results from the first part in order to inform how much to use in the second part. Okay, moving on. So sodium sulfate solution is also formed when sodium hydroxide solution reacts with copper sulfate solution. Give a balanced symbol equation for this reaction. Okay, so we've got sodium sulfate. Now, sodium sulfate, we could just remind ourselves, is the formula for sodium sulfate is down here, so we don't need to refer to the table of ions in the back. So Na2SO4, and then that's going to react with sodium hydroxide. Okay, I'm going the wrong way around, rushing. So I'll write it at the bottom here so that we've got plenty of room. Okay, so we'll do again. So the sodium sulfate is the product. Okay, so sodium sulfate solution is formed. So that's Na2SO4. Okay, so we know that from the previous question. And then we also need to put in that we've got sodium hydroxide. Okay, now sodium hydroxide, you may remember sodium hydroxide, but just in case, if we refer to our table of ions, sodium ion is Na+. So there's a sodium ion. So just to go through the process, we need steady on, Na+, and the hydroxide ion is OH-. So if we apply the seesaw principle, we can see that those two balance each other out. So the overall formula is simply NaOH. Okay, so that's the sodium hydroxide. And then it reacts with copper sulfate, okay, which you again may be familiar with, but just in case, let's go to the back page. So copper is here, Cu2+. So we've got Cu2+, and the sulfate ion is there, SO4, 2 minus, and as far as the ions are concerned, in our seesaw, our balance, we've got a 2 plus and a 2 minus, which automatically balance or cancel each other out, giving us the formula CuSO4. Okay, so that's CuSO4. And so we can see that we've got the ion, the sodium is used, but we've got nowhere on this side where the copper is used. So there must be another compound that's not mentioned in the question, okay, which we need to sort of work out. And so as this is an exchange of ions, basically, so the sodium ions end up with the sulfate and the copper ions end up with the hydroxide. But there's a small complication because we need to double check the formula. So if we go to the back, again to our table of ions, and we remind ourselves that copper is Cu2 plus and hydroxide is OH minus, then we can see that we'll need another hydroxide ion because this is 2 plus, although you can't see because it keeps going through the paper, and these are minus each. We need 2 of these, so we need 1 copper ion and 2 hydroxide ions, which gives us the formula CuOH2. Okay, so as it's what's called a compound ion, it's got more than one atom involved. We have to put the brackets around it, and we put the 2 at the end. Okay, and so we've replaced that in our equation here, copper hydroxide, and then we look at balancing this. Now we've got 1 sodium here and 2 there. Okay, so we can put the real 2 there, and then as it happens, that does actually solve the problem because we've now got 2 hydroxide ions on this side of the equation and 2 hydroxide ions on that side of the equation as part of the copper hydroxide, and actually the coppers and the sulfate ions are all balanced automatically. Okay, so that was worth 3 marks because you did have to work out the formula of that, and you also have to balance the equation in the end. Okay, so that one was a slightly more difficult balancing. Slightly more difficult balancing equation. Okay, and so let's move on to the next question. So it then says, describe tests that can be carried out to identify both ions in sodium sulfate solution. Give expected observations for both tests. So when we're trying to identify metals, invariably we're talking about the flame tests. Okay, so for sodium, it's a flame test, and the positive result for the flame test is a yellow flame. Okay, so or a yellowy orange flame, but a yellow orange flame, which realistically is not difficult to, so it's not easy to spot because it looks a bit like a Bunsen burner flame, but it's a yellow orange flame. So if you're not sure about the flame test, if you dip a wet splint into a solution of the sodium sulfate and then place it in a flame briefly, the flame will go a yellow-orange color. And then for the sulfate, okay, so it's not a flame test, it's a chemical test. We need barium chloride, so barium chloride, and when you use barium chloride, it reacts with the sulfate ion to make barium sulfate. And barium sulfate is insoluble and it's white, so we get a white precipitate. So a white precipitate of barium sulfate is formed. So the sodium sulfate is a clear and colorless solution. You add the barium chloride, which is also clear and colorless, and the mixture produces a white precipitate, and that's due to the presence of the barium sulfate ion. Barium sulfate compound, which is insoluble and therefore precipitates out. This next question. The reaction occurring between solutions of sodium carbonate and magnesium sulfate form a precipitate of magnesium carbonate. Right, the ionic, okay, so it's important that we see that word there, equation for the formation of magnesium carbonate. So the magnesium ion, we could refer to the back, but I'll save us the bother, is Mg2+. And the carbonate ion, because it is an ionic equation, is CO3 2-. Okay, These two automatically cancel each other out, so we can then move straight on to writing the formula MgCO3. So it's basically the same process as we've gone through a number of times at the back of the book. These things here, but written in a slightly different format. Okay, it's just a simple equation. Right, number 6 looks like a very daunting question, okay, but some aspects of it are simply a comprehension. Okay, so it says in 1985, a new allotrope of carbon was discovered and named Buckminster fullerene. This allotrope, okay, so allotrope is forms of the same element, so different physical forms of the same element. Consists of 60 carbon atoms joined together to resemble a shape similar to that of a football. Okay, so just in case you know what a football looks like. Only 10 septillion, okay, so that's 10 septillion times smaller. Okay, so this is a lot smaller than a football. This form of carbon was named after the architect Buckminster Fuller, famous for designing geodesic domes as shown in figure 2. So unfortunately in this copy of the paper it's not very clear, but it's a great big greenhouse basically. Key bit of information there, that Buckminster fullerene is approximately 1.1 nanometers in diameter. The structure of the Buckminster fullerene is a truncated icosahedron, okay, consisting of 20 hexagons and 12 pentagons that intersperse to form a spherical structure. Within the structure, each carbon atom is bonded to 3 other carbon atoms, okay, so that's quite significant, and no pentagon has a joining edge with another pentagon. Okay, so all the pentagons are surrounded by hexagons. So just bear that in mind, it's got 3 carbon atoms. So does it have a delocalized electron, as it's got only 3 of its electrons involved in bonding? Anyway, other spherical allotropes of carbon called fullerenes have since been made. These include balls consisting of 70, 76 or 84 carbon atoms. Together they become known as buckyballs. Fullerenes have high melting points and boiling points. They also have a high density and a large surface area for their size. Today, fullerenes are at the heart of nanotechnology, the study of atomic scale structures and devices. This provides many exciting new research possibilities for scientists, including their potential use in catalysts, lubricants, and in nanotubes for strengthened materials and as a way of delivering drugs into the body. Nanotubes are fullerenes that are used to reinforce graphite in tennis rackets because they are very strong. They're also used as semiconductors in electrical circuits, so that there sort of backs up the delocalized electrons. The nanotube structure also allows it to be used as a container for transporting a drug in the body. A molecule of the drug can be placed inside the nanotube cage. This keeps the drug wrapped up until it reaches the site where it's needed. In this way, a dose that might be damaging to other parts of the body can be delivered safely to, for example, a tumor. Okay, so it's quite a lot of information there. But if we move on to the actual questions, so the first one, tick all the statements that correctly describe Buckminster fullerenes. Now, it doesn't actually tell you how many statements to tick, but there's actually a bit of a clue there. So in questions like this, if you've got 2 marks, the likelihood is there are 3 correct answers, because they tend to give you slightly less marks than ticks, okay, because ticks are looked upon as being a little bit easy. Now, its structure has 32 faces. Now, it doesn't actually tell you exactly how many faces it has, but it does tell you it's got 20 hexagons and 12 pentagons. And so if we look at the diagram, okay, we can imagine that 20 hexagons and 12 pentagons, which of course is 32, then there are 32 faces. So that first statement is true. Okay, it has a relative molecular mass of 60. Okay, now if it was 60, it would only contain 5 carbon atoms. Okay, and these don't contain 5 carbon atoms, they contain 60. So that's not true. It's an allotrope of carbon. Okay, well, it is an allotrope of carbon. Other allotropes of carbon include graphite and diamond, but those are not mentioned here. It is a giant ionic structure. Okay, now as it consists of carbon atoms and carbon atoms only, it's not ionic. Okay, it's a covalent structure. It's a hydrocarbon compound. Well, it only contains the carbon, no hydro. Okay, so it's not a hydrocarbon, no hydrogen. It is a smart material, and I've given some of the uses that it's been suggested in there. Then we can assume that it is indeed can be classed rather as a smart material. Okay, so we'll take that one in a second. So it is a smart material. Oh, sorry. No, it's not a smart material because it doesn't change its structure or behavior. My mistake. Okay, so smart materials, they tend to things like shape memory alloys and shape memory polymers. They actually change under different conditions, whereas it doesn't change. Some of the uses it's been put to are quite interesting and quite advanced, but technically it doesn't count as a smart material. Okay, however, it is a 25th time smaller than a football. Okay, as illustrated up here. Okay, so that last one I was almost drawn into that, but it's not a smart material because of the definition of a smart material. Right, part B, use the following formula to calculate the number of edges that a molecule of Buckminster fullerene has. So the number of edges is the total number of sides of all pentagons and hexagons divided by 2. So if we take the numbers in our information, we've got so the number of sides on all pentagons and so we've got two sums to do. We've got 20 times 6 plus 12 times 5. Once we've got those values, we divide the whole lot by 2. Okay, so as I say, you can always have a calculator on hand just to make sure you get the answer spot on under the pressure of exams. So 20 times 6, it's not surprising, is 120, plus, we'll put the brackets in case this calculator doesn't follow BODMAS, 12 times 5, close that. That gives us 180, and then if you divide that value by 2, it won't surprise us to learn we get the answer of 90. So the number of edges is 90. Okay, so as is always the case in these, if you write your calculation out and the answer, that's your 2 marks. If you make an error in your calculation, but if you actually write the calculation out correctly but make an error, you still get a mark for that, even if you didn't get the mark for the final answer. Right, now this next one is a bit cheeky. It's very, very much from the numeracy aspect of the syllabus. So it says calculate in meters cubed the approximate volume of a Buckminster fullerene molecule. Write your answer to 3 significant figures in standard form. Okay, so only 3 marks. So we're told that the volume of a sphere, okay, is 4/3 pi r cubed. We're told to use pi only to 3.14, so we don't want to be using the pi value in our calculators. We're told that r is the radius, and we're told that 1 nanometer is equivalent to 1 times 10 to the minus 9 meters. What we're not told here is what the radius of a Buckminster fullerene is. However, if we refer back to the original information, we're told that the diameter is 1.1 nanometers. So if the diameter is 1.1 nanometers, I'm sure from maths you know that the radius is going to be 0.55 nanometers. Okay. Now, if we use that value now and put it into our equation that is given in the question, so if 1 nanometer is 1 times 10 to the minus 9, and we're going to cheat slightly because we're not going to write this in standard form just to make life simple, then our buckyball has got a radius of 0.55 times 10 to the minus 9. Okay, now you're confident with standard form, you could convert that into proper standard form, but it should work in our calculation. So our calculation is going to be 4/3 times 3.14, because we just need to use that value for pi, times, and then we're going to put, this needs to be the radius of our buckyball is that value. We need to cube that, okay, because we need to cube it according to the equation there. So if we put that in, so we've got, let's cancel everything, so cancel. So 4 divided by 3 times 3.14 times, and to be on the safe side, let's put this in a bracket. So we've got 0.55, and this calculator has got a standard form button, and this is 9 minus, and if we close that, Oh. And it's not going to accept that, is it? I'll tell you what, I'm going to do it in reverse so that we don't fall foul of this calculator. So we'll do the hard bit first. We'll do this bit first. So we've got 0.55 to the power minus 9. Okay, and then if we cube that, so we use this function here, to the power 3. Okay, and then we then multiply that by 4, divide by 3, and multiply by 3.14. Okay, so that gives us the raw answer 6.965 times 10 to the minus 28. However, it does ask us to quote it to 3 significant figures. We need to be careful there. So 3 significant figures is 6.97. Okay, so 6.97 times 10 to the minus 28 meters cubed. Okay, so just need to be careful how you use your calculator to make sure that you calculate out this bit here correctly. Right, give the main reason why the structure of fullerenes has resulted in there being an interest in developing their use as catalysts. So if we have a quick look back at our information here, somewhere in here it tells us that they have a large surface area for their size. Here we are. They have a high density and a large surface area for their size. So catalysts work much better if you've got a large surface area for the chemicals that are reacting to react upon. Okay, so large surface area. And then state why some people might oppose the use of fullerenes in drug delivery systems in the body. So this is similar to the issues with titanium dioxide in sun cream as a nanoparticle and also silver as a nanoparticle. Short-term studies have shown them to be safe, but long-term studies might show that to be some issue. Okay, so long-term use could, we don't know certain, be dangerous. Okay, so the studies, because they're new materials, it's possible that we need to use them a bit longer before we can be sure of their efficacy there or the lack of issues. One student said that buckyballs should be good electrical conductors, but her friend disagreed. Use your knowledge of bonding and structure to give one reason that each student could use to support their argument. Okay, so we've established earlier that they've only got 3 bonds. Each carbon only got 3 bonds, which means that there will be delocalized electrons in their structure. So delocalized electrons in graphite do allow graphite to conduct electricity. So delocalized electrons allow, that would be a reasonable assumption that they can conduct. However, unlike graphite, buckyballs are discrete molecules. They are not giant structures. They are small covalent molecules, and therefore that movement of electrons can only happen within the structure and can't happen within a larger body. Okay, so they're not giant structures like diamond and graphite. They are discrete molecules. So no large-scale conduction. Nanotubes are thought to may be a way forward, but the nanotubes and buckyballs are different. And then if we move on now to the final question, okay, which is a 6-marker. Okay, now as is the case in all 6-mark questions, the examiner will band your answer. In other words, put it into 3 categories in terms of your communication, but then also, so the better you communicate, they will be in the higher band, but also they are looking for your chemical knowledge. So discuss what is meant by isomerism in alkanes and alkenes using compounds with the molecular formula C4H10. So from its formula, we can recognize that as the alkane because it fits the general formula CnH2n plus 2. And C4H8, that's going to be an alkene, as it fits the formula CnH2n. Okay, so first of all, you need to establish with the examiner you know what isomerism is. So isomerism is different structures or the same formula. Okay, so the same formula. And for this particular question, I would suggest the best way to explain that is to give examples. Okay, so if we take C4H10, remember in the real exam this will be twice as big at least, so you have a bit more room to play with, and also you do have lots of room on the following pages should you need it. So C4H10, the simplest version of that is simply 4 carbons in a row, and surrounding those carbons would be the hydrogens. Now, if you have time in your exam and you want to be a bit neater, you can draw in the hydrogens, but basically that shows the structure, and that is simple butane. Now, the question doesn't demand that you name everything, okay, so you just need to show that you understand that isomerism is different structures for the same formula. So if we take this structure and then we simply reduce the carbon chain length to 3, we can then place the 4th carbon on there, and then if we double check that we've got the right number of bonds in there, then that shows 2 different structures for the same formula. Okay, we can't really do much more with that because we can't put the carbon anywhere else. If we were to place it on either of these end carbons, we'd end up back where we started, and if we move that carbon to the top there, all we're doing is rotating that structure in space. So those are the 2 isomers of C4H10. C4H8, okay, is a slightly different kettle of fish because it's an alkene, and so we recognize it as an alkene. Actually, before we move on, we should state that that's an alkane, and we could name this one as butane to make it clear that you understand the simple formula. So that's butane there, because it's got 4 carbons, but, and it's got no double bonds, so it's an alkane, so it's ane, and it belongs to the alkane family. This, however, this is an alkene. We can recognize it as an alkene because it fits the general formula we mentioned before, and this is going to be butene, or the simplest version of it would be butene. And butene is 4 carbons in a row, and the simplest version of butene, we'd put the double bond between the first 2 carbons like that, and then we make sure that we've got the appropriate number of hydrogens on there. Okay, and if we just double check on the end of each of these bonds, we would have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, which fits our formula. But this question's about isomerism. Okay, so we need to change this in some way. So the next thing we can do is take that double bond and place it in the middle of the molecule. And again, we have to be careful. Each of these 2 carbons has got 3 bonds on it already, so we need to add an additional bond. It doesn't matter whether it's above or below. But again, if we just double check that we're matching the formula, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that does match the formula, but it's a different structure because we moved the double bond along 1. Okay, and then there is one other way we can mess with this structure. Oh, sorry, not mess with, change this structure. We can't move the double bond to there because in doing that we're simply recreating this. We're taking that and flipping it over onto its head. What we could do is take this carbon on the end and place it somewhere down the carbon chain. So I'm going to open the book, the next page. And so I'm going to draw 3 carbons in a row. I'm going to put a double bond there, and then for this carbon here we're going to put the 4th carbon, and then we'll just add in the extra hydrogens. So this carbon has already got its 4 bonds, we don't need the hydrogen on that one, and then we'll add the additional bonds on here. So we've got 4 carbons, and then we've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Okay, so that is a third isomer of that structure there. Okay, of the butene. And as I say, you don't need to name them all. This one here is what we know. It's actually but-1-ene, but and this is but-2-ene. But that's not what they want to know. They want to know that you understand that isomerism is a different structures for the same formula. Okay, so that there. Just about finishes. So just for completeness, we will give the names. So this one here is butane. This one here is methyl propane. And it's methyl because you've got a methyl group on a 3-carbon chain. So 3 carbons is prop, and then methyl is the 1 carbon there. This one here is but-1-ene. And it's but-1-ene because what we do is we number the carbon chains with the smallest number 1 nearest the end with the item of interest, the functional group we call it. So a functional group in this instance is the double bond. Okay, so that's but-1-ene. We do the same here. Now for this one, it doesn't matter which end we number from because we end up with the same results in either direction. So we might as well number from this end. 1, 2, 3, 4. And in naming it, we use the smallest number. So that's but-2-ene. And this one here is, we've got a carbon chain of 3. Okay, so we've got methyl, that's the methyl group there. And this is 3 carbons in a row with a double bond propene, methyl propene. Okay, so those are the isomers for those 2 different formulae.